In the name of Allah. In this tutorial I am trying to implementing a friction problem using ABAQUS software. Firstly, I am calculating the problem using hand calculations, and then we will implement it in ABAQUS. This is the problem. We have a concrete block. The dimensions of our concrete block is 2 meter by 1 meter and 1 meter. It means that our concrete block is 2 cubic meters, and a pulling bar made on steel fixed with the concrete block, and this pulling bar is used for pulling the concrete block on a ground surface. Also the ground surface is concrete. uh, of course we have a density for our concrete. Its density is 2.55 ton per meter cubic meter, and the mu, or coefficient of friction between the two surfaces, is 0.5. Okay, and also we have a top surface pressure uh, on the top of our concrete block. Its pressure is 0.475 megapascals. It means that our pressure is about 0.475 multiplied by 2000 and multiplied by 1000 millimeters, and divide by 9.806 and divide by 1000. Our pressure is about 97 tons. 97 tons of loaded here. Okay, the question is that the problem is find the normal stress in the pulling bar between the when the force F causes the block to move. We have to find the normal stress. Of course, the stress is tension. Normal stress in tension is this bar, and we have to find the stress in this bar. Firstly, we have the friction formula, F equal to N by mu. N is the total load that acting vertically, and the mu is the coefficient of friction, and the F is the force that causes the block to move forward. Of course, N is the density plus the pressure. Density of the concrete block, we can find it using multiplying the density by the 1000 for converting tons to a kilogram, and then multiply by 2 because our block is 2 meter cube, and then multiply by 9.806 for converting the kilogram to Newton, and of course plus the pressure. The pressure multiplied by the surface area, which is 2000 by 1000, and the total normal force is equal to 1 million newtons. Thus F, the friction force, equal to 1 million multiplied by the mu, which is 0.5. Thus we get 500,000 newtons. And now, because we determine the F, thus we can determine the stress in this pulling bar by dividing the F by the area, cross-section area of the bar. Of course, cross-section area, we have the cross-section area, the dimensions of this bar is 100 millimeter by 100 millimeter. Thus, finally, we get the normal stress is 50 megapascal. Okay, now we are going to ABAQUS for implementing the problem. I'm using ABAQUS 2020, but there are no difference when you using an older version. Firstly, I am defining parts. The first part is concrete block. Okay, the dimensions of our concrete block is 2000, 1000. Of course, I'm using millimeters, and 1000. Okay, and the second part is ground part. Of course, the ground part, for the ground part I'm using the dimensions should be greater than the concrete block. For this direction, I'm using 3000 by 2000 and 1000 millimeters. And the third and final part is pulling bar. $100 millimeter and 1000 millimeter by 100 millimeter. Of course, we now going to material. We have concrete, but firstly we should using the ABAQUS consistent units. I'm using this column for the density. When I'm using this column, I should use ton by ton divide by millimeter, cubic millimeter for the density. Thus, my concrete material density is 2.55 E minus 9. And for the, of course, elasticity should be defined. For example, 25,000 megapascal and 0.24 Poisson's ratio. And now I'm defining steel material. Density of steel is, but because I do not calculate the density of the steel bar to my hand calculation, thus I'm entering here only 0, and the density of steel 200,000 and Poisson ratio may be 0.25. Okay, steel, steel, okay, and concrete, concrete, okay. I'm defining the material. This is steel, of course, and other parts are concrete. Okay, now I'm going to assembly section, selecting all parts, and I'm rotating the ground by 90 degree, and then translating the parts to their right position. Here is okay. But firstly, uh, we have to cutting the section of our concrete. Partition face, this face, and this edge. The steel bar dimension is 100 by 100, and the distance from here should be 450 millimeter. For the side is same, for locating to the center of the block. Okay, okay. Step, I'm using static general, and dividing the increment, then interaction, friction 0.5, contact, name must be friction contact, tangent behavior, not friction legs but penalty, and the coefficient of friction is 0.5, and normal behavior hard contact. Okay, now defining this contact to its right position. Contact, surface to surface contact standard, because I am using standard solver. Select it here, done. And for the slave surface I should use the other surface of the concrete block. Parts, concrete block, replace, okay, surface here, done. Of course there are no problem for master and slave surface, because they are the same material, and we have another contact, which is the pulling bar should be tight with the concrete block. Here uh, constraint constraint 1 tie should be tie for master surface. I'm selecting the concrete block, and for the slave surface I'm using the pulling bar surface. Okay, master surface also there are no any problem, I think, between the master surface and the slave surface. And loading loading and boundary conditions. Of course, the base of the ground should be fixed based boundary. Continue here, done in cast tree. Okay, and I'm using lateral displacement 10 millimeter displacement, 10 millimeter displacement for this surface, done. Of course, in the X or one direction, 10 millimeter. Okay, and the finally mesh. But first I should go to the part section and divide this part for making a best mesh option. We have to partition cell using this icon and by normal to each point, normal to each point, normal this point and this normal, enter. Again I'm selecting all point, normal this point and this normal. Okay, and this point, this normal. Okay, finally this point, this normal. Okay, very good. Now for meshing, first part I'm using 50 millimeters, yes, and the element type is 3D stress standard linear. Okay, we do not change anything. For the other parts I'm using same mesh size, 50 millimeters. Okay, done. Yes, for the pulling bar same. Yes, assembly. The nodes of each mesh, we see that they are coinciding each other for their right position. Okay, now I think our model is ready for run. uh, Create job, but firstly I'm saving the new directory, saving the model friction test. Friction test, okay, and the civil directory should be same place. Okay, okay. Now creating the job, the only option I edit here is multiple processor. I'm using 6 processors because my computer has 7 cores. Submit. Submitted. Running. Monitoring. Completed successfully. It may take several minutes. It's the warning. The person is there are no problem. The problem submitted at this time, but may it takes several minutes. That's why we are waiting until the end, and then I'm now stopping the recording. We will then resume it. But before completing the analysis, I stopped the analysis because I forget to assign the pressure load to the top of the surface of the concrete block. Here we are defining the pressure first step, but I think still we have step 1. Okay, load, pressure, continue, the surface, this and this. Okay, done. 0.47475. Okay, another job. We have to define another job. Okay, and the directory is submit. Submitted. Monitoring. Complete successfully and submitted at this time. After completing the analysis, I now pause the video, and after completing the analysis, I resume it. Pause. Now the analysis was completed. This is the iterations completed at this time. Okay, results. I'm showing you the results. Primary stress S11. Okay, and you can see that the maximum stress is about uh, 47.6 and located at this point. As you see, all the bar is in red color, and the stress is about 47.6 megapascals. Of course, the stress is S11, stress in X direction, and the result is very near to the hand calculation. It was 50 megapascals. This is all about our tutorial. Thank you for watching.